Ooh, welcome back. We got a fun little stretch of our brain coming up with this question. Let's see what we got. So the statement reads, find x as a function of t for motion starting from rest at the origin under the influence of a constant Minkowski force in the x direction. Leave your answer in implicit form, aka t as a function of x. Okay, so we have a Minkowski force in the x direction. Let's see what we got. This being said, we had to review what the Minkowski force was. So let K be the constant Minkowski force. Then we say that K is equal to dp d tau. Via chain rule gives us dp dt, dt d tau. And so we see that we have dt, d by dt of the position function, or the ordinary velocity of momentum, times the dt by d tau, which gives us the gamma factor that we need for the relativistic case. However, what we're trying to do is do a little more tinkering with this. So let's keep this u and this square root over here, bring this m and this stuff over, so multiply that over, divide by m, and we see that we get k on one side and d by dt on the other. Why do we want to do that? Well, we're trying to integrate, and since we know that u is equal to dx dt, we can multiply dt by dx is equal to 1 over u, and as you see now we get a constant separation here, or excuse me, we can move things around in order to get a much more advantageous position for solving the equations. Multiplying both sides, yeah, by u. Yeah, so you see the blue goes to the left, red goes to the right. The dt's cancel, and we're left with d by dx. Again, this is all for just trying to solve and integrate down. So again, a bit of a tricky mess to deal with. We'll go ahead and let the substitution of w equal u over the square root of 1 minus u squared over c squared. So we have 1 in both of those, and then we can see that this substitution cleans it up slightly. So we have k over m times 1 over w is equal to d by dx of w. So let's get all the w's to one side. Here we have, once we do that, we get km by itself, so we have w times dw dt, or dw dx, which we can unfold as a 1/2 d by dx of w squared. We got to put the 1/2 there in order to combine them into the square again. So we can multiply that over, no big deal. Once we do that, then we can kick this to the left-hand side, and now we can integrate both sides, where we know that dw squared can be undone here. Then we can undo dx there, so we're left with w squared equal to 2k over mx plus a constant. We're told it is that at t equals 0, x equals 0, and u equals 0 as a result. So w has to equal 0, and therefore the constant is 0. We're still not quite done yet, so now we have to solve a way for w here. Plug it in. We got a whole bunch of stuff for u's. Let's condense it down and simplify as best we can. Get this factor over, distribute, and then we'll consolidate on the next slide, getting all the u's to one side. Boom, that's what we do here. And then naturally we have to factor that u out and then redivide. So that's what we have here. As you might imagine, they have a couple things that we could force factor out and cancel along the way. That being said, we have a 1 over c squared thing here going on. So we could just, since we're dividing by a fraction, multiply by the reciprocal and try to tidy up as best as we can. That being said, we know that u squared is equal to dx dt in a square, of course, so we're going to have to do a square root on everything. Makes it even more juicy. Clearly, this thing is gross, and more gross. And then, of course, if we want to do separation of variables on this thing, dt goes over there with the c, and everything over here that has an x term right there in the middle of that square root, that has to go on the dx side. So now we're left with the integral of the square root of 1 plus this purple term, which we're just going to rename into another constant. We'll call that a squared. And then we'll go find an integral table for this because it is gross. That being said, you see we can kind of do the force factor method again. And then we're left with a split square root now. let x equal y squared, dy equal this. So just do a substitution on it. Again, all of this is a bunch of fancy algebra. You could use an integral table. You could use a machine to do it for you. But the substitution route is pretty cool to see. So let's see how it manifests itself now. That being said, we get CT, and then we see that the substitution cancels out a lot of stuff. And now we can integrate this nasty looking thing here. And again, we have to be able to separate the fact that we have a constant of integration that we need to solve for, which we can do with t0, x0, therefore y equals 0. And so we see that the constant is equal to, once we plug all these in, with the left-hand side equals 0, if we plug in t and x and y equals 0 into the appropriate spots, we see that the constant is actually equal to negative a squared ln of a. So we get a big old nasty looking equation for CT, and of course we can go ahead and tidy up somehow. That being said, multiply a by a here just to get everything settled down and canceled out. You can do as much as you can, but there is a way of simplifying this that is so gross, you're kind of looking at it. So I'll let you read through the algebra here, but I think we know how all this ends up. And then, of course, after we're done back subbing everything in from the original a substitute, then we can let z equal y over a, and then let all of that trickle through, and we can see what cancels out. The implicit form of this constant Minkowski force is 2kt over mc is equal to z square root z squared plus 1 plus ln of z plus the square root of z squared plus 1. Holy moly, what a mess. I think we know from differential equations that we could conceptually tear through this. Separation of variables. That part's not too hard. A hard part, of course, comes in all the algebra and the calculus substitutions. But I think we know how to get there conceptually. Putting the work in, that's where the mess comes in. But that being said, cool result. I believe it's used somewhere else, but I'll put that in the footnotes or the description. And yeah, we'll see you at the next one.